have told you in the Davisson Germer experiment the principle and the diagram. In diagram we have the four parts. One is the electron gun, second the nickel crystal, third the ionization chamber, and fourth the semicircular escape. Now today I will tell you the working of this experiment, the observation, calculation, and final the result. As I have told you that the electron gun provides the accelerated electron beam, and this electron beam falls normally on the nickel crystal, which diffracts the electron beam, and this diffracted electron beam is received by the detector, where it ionizes the gas and the current is produced, which is measured by the galvanometer. That gives the intensity of the diffracted electron beam. Working. The collimated, fine, accelerated electron beam is provided by electron gun. This is what the action of electron gun. The accelerated electron beam falls normally on nickel crystal, which diffracts the beam and it is received by detector. The diffracted electron beam ionizes the gas in detector and a current is produced by ice which is measured by sensitive galvanometer. Sensitive galvanometer. The intensity of the diffracted beam, intensity of diffracted electron beam is proportional. This is proportional to the current due to ionization of the gas. So larger the ionization, larger the current, and larger is the intensity of the diffracted electron beam. Range of accelerating applied voltage. This is equal to 44 volts to 68 volts. The electron beam is accelerated from 44 volt to 68 volts, and the angle of diffraction ranges from 0 degree to 54 degree, 0 degree to 90 degree. This is the range of angle of diffraction. So now for each accelerating voltage, the electron beam is diffracted by the nickel crystal, and the detector is placed at the different position on the circular scale, and the intensity of the diffracted electron beam is measured by the galvanometer at all F value of the angles. For a given accelerating voltage, the intensity of diffracted electron beam is measured at different positions of detector on the semicircular scale. Suppose the accelerating voltage is 48 volt. Then the electron beam will strike on the nickel crystal. It will be diffracted. Then this detector is placed, suppose at some angle, then intensity of diffraction is measured. Then it is moved to another angle, and then again the intensity of diffracted beam is measured, then kept on the next position, and again the intensity of diffracted electron beam is measured. So thus for a given voltage, the detector is placed at the different positions, and the intensity of the diffracted electron beam is measured, and finally a polar graph is plotted. a polar graph is plotted between intensity of diffracted electron beam and angle of diffraction. Angle of diffraction. So the number of graphs are obtained for different accelerating voltages. So the polar graphs are like this. Now we come to observation. In observation, what we find from this experiment, that for a voltage of 54 volt and the angle of diffraction is 50 degree, then the intensity of diffracted electron beam is measured. Experimentally, it is found that for 54 volt accelerating voltage, the maximum intensity of diffracted electron beam is found at angle 50 degree. So now that if we draw the polar graphs, then these polar graphs are like this. This is, suppose I take here is intensity. Intensity on this side, and here we take the angle. This is now, suppose your 40, this is now 48 volt, and here we take the angle theta. Then it is found that it is to be like this, and when we take it in this way, this is the intensity and here we have the angle theta. So angle theta, this we have taken for, suppose it is your 46 degree, and here we take this, the polar graphs to be like this. Suppose this we take the angle, this is now your 48 degree, and the accelerating voltage, suppose now this is now, suppose we take 46 volt, this is now we take 48 volt, and then we get the graph. This is suppose now 50 volt. Here we take angle theta, here the intensity. And then we find that the graph is not to be like this. This is the angle of diffraction, suppose this is now your 49 degree, 49 degree, and then suppose we are having the graph like this. This is now suppose intensity, and this is now your theta on this side, and this we take 54 volt. Then this is found that the intensity is very large. This angle is 50 volt, 50 degree, very high. And now again we increase to this one. Suppose I take the graph like this. This is now intensity. And this I take the theta on this side. And suppose now this is 58 volts. Then the graph is like this. Like this. This angle is somewhat larger. So this is for about suppose 54, 55 degree. Then like this we are getting the graphs. So we can see that larger peak occurs for the accelerating voltage 54 volt and the for angle of diffraction 50 degree. So in polar graphs, the sharp peak occurs at 50 degree and 54 volt. So now from this is the observation, this is our observation that for so much angle and so much accelerating voltage the peaks are maximum. So this is the what the maximum, and for any other angle the peak is not so much high. Because of that we find that the diffraction is maximum when this is accelerated with 54 volt and diffraction takes place at 50 degree. So now we calculate. Now calculation. Calculation. Now we are having by Black's law as I have told you earlier, this 2d sine 90 degree minus 5 upon 2 is equal to L. So for first order diffraction, now this n is equal to 1. Therefore, lambda is equal to 2d sine 90 degree minus 5 upon 2. 5 is the angle of diffraction. This is given to us 50 degree. So now you use it. This is now your 2d. Now the value of d, this is equal to 2 into 0.92 angstrom into sine 90 degree minus 50 degree upon 2. This is not so much. That we are given this pi is equal to 50 degree. So this is 1.84 angstrom into, this is now sine 65 degree. Sine 65. And this is 1.84 into 0.90. So this is equal to 1.66. 1.67 angstrom. So much. If you just multiply, .84. And now this is the theoretical value. It is theoretical value. It is, no, it's not experimental value. Experimental value of lambda. Now theoretically, de Broglie wavelength, now this is lambda equal to 12.27 upon square root of b. This is not so much angstrom. Now this is 12.27 upon square root of 54 angstrom. 54 angstrom. And this value is coming out to 1.66 angstrom. This is equal to lambda. Now here what we have used, so this is the theoretical value and this is experimental value. Here d equal to 0.92 angstrom, the interplanar spacing. Interplanar spacing for nickel crystal. And this we have known that this phi is equal to 50 degree, and this is now b equal to 54, that we have known to this one. So this is now experimental, this theoretical value, this is the experimental value. So now we come to the result, and we see that this theoretical value resembles with the experimental value. This is now 1.67, this is now 1.66. So it is in very good agreement. So we can see that this confirms the existence of matter waves associated with the accelerated electron beam. So how I have shown to this one that this is like this. This is now suppose your atomic lattice. This is now first plane, this is now second plane, this is now third plane. So what I have is that this is now incident and this is now diffracted. So this angle is phi. This phi is equal to 50 degree. 50 degree. This is now value of D. This is not D. This is so much. This is not D. The interplanar spacing of this crystal lattice. So this is the angle of diffraction phi. So this what we have obtained that from so much this is now so, and this D is given to us 0.92 angstrom. This is known to us. Now we come to this is the incident electron beam. And this is diffracted electron beam. This is the angle of diffraction. So now we come to result. What we see that the theoretical value and the experimental value are in good agreement. The theoretical and experimental value of wavelength are in good agreement. And this confirms the existence of matter waves associated with accelerated electron beam. Accelerated electron beam. So it shows that there are the matter waves associated with the moving particle. This experiment is the first one which gives the confirmation of the matter waves. Though before this one, the confirmation also was done by G.P. Thomson, the son of J.J. Thomson, and he made the diffraction of the X-ray of this electron beam also. But this is more important because this is based on the Bragg's diffraction law. So this is what that this experiment is most important for the confirmation of the matter waves. So this I have told you that how does this existence is confirmed by this experiment. And for this one, that when this was confirmed experimentally, that de Broglie was awarded Nobel Prize in Physics in 1929. So this is about the working and the observation, calculation and the result of the experiment. Now in this experiment, whole experiment is never asked in the board exam. Only some parts are asked. For example, what is electron gun? What is nickel crystal? Why do we use the nickel crystal? And what is the sense of detector? Or simply the name the parts of the Davisson Germer experiment, the working of the Germer experiment, the calculation, what is the result of Davisson Germer experiment. So like this the questions are asked. So you have to answer the question according to the level of the question. So do not write any vague answer, so that this becomes very much unclear, and also the marks awarded to you will be equal to 0. So always remember that you have to answer according to the question. So thank you very much. You all like, share and subscribe the video. Thank you very much.